Today we are looking at another way of using calculus to find volume of figures. This is a method called volume by rotation. Specifically, this is what's referred to as the disk method, as compared to the washer method. That's what we'll be talking about tomorrow. You probably won't understand the difference between the two until we do the washer method tomorrow, but just know that those are both types of volume by rotation. So the idea here is we're going to be finding volumes of shapes that look something like some of these things you see here. What you should notice is these figures are all round around the outside. Okay, they could be constructed by rotating around an axis. So they're not perfectly symmetrical. Okay, in terms of, like, if I were to draw a line right here, these are very irregular. Okay, but I could take a line down the middle like this, and actually I'm going to draw that line in here. I could take a line like this and spin it around that line, and this thing would retain its shape. Okay, so if I wanted to do this by rotation, what I'm going to do is put this line in here, and that's like our x-axis. Think of that as the x-axis. And then I'm going to define a function, or be given a function, that would give me like this curve right here. Okay, so if I could come up with some function that would give me that curve right there, then I could use this method to find the volume of this figure. Because what I would do is I would grab any point on that function, and then I'm going to grab this thing and spin it around the x-axis. So I'm going to kind of spin the function like this, and that's what's going to form my figure. So when I take this one point and rotate it, it's going to form a perfect circle. It's going to go over here, and then it's going to come back up the other side, and my drawing is not nearly as good as the picture down below. But I'm going to do that with every single point on this function, and I'm going to form a bunch of these circles. Otherwise known as disks. Okay, so that's where the disk comes from, is we're making a bunch of these flat circles with the points on the function. So I'm going to use this image down here because my artwork is not nearly as good as this. So this blue function would have been the function that I start with, my f of x. And I'm taking this and rotating it around the x-axis, and it's giving me this shape, sort of like a vase, okay, if you imagine it on its side. So if I want to find the volume of this thing, what I need to do is find the area of all of these individual disks or circles. Okay, so this thing here is going to have an area of pi r squared. And then what I'm going to do is I'm going to integrate the pi r squared from n to n. So maybe this value here is my a value. And let's see where the end of this function is. This value here would be my b value. And so I'm going to integrate from one end to the other and add up the area of all of those circles. Okay, just like we were doing before. The biggest difference here, though, is what is our r? What is our radius here? Well, the way this circle was formed, because when we did cross sections, our radius or our diameter was the function itself. But this time, this point off this function is traveling around to the other side of the axis. So when I draw in just the radius is just that length there. And that length is between 0, this number here is 0, and the f of x function. So this point would be f of x. So in this case, our radius would just be f of x. Okay. Now, there are times when we use axes other than the x-axis, so this might be some other number besides 0, and so then we might have to do f of x minus 4 or f of x minus 2, depending on what axis we're spinning around. But if it's just 0 and you're doing f of x minus 0, then your radius is just f of x. So I've got this written up here in this box for you, almost like a formula. When we're doing this solid by rotation here, we're going to do this by integrating pi r squared, just like what I had down here, except I moved the pi out front. And then for this radius, down here, there's a note here, is the distance between the function, which is f of x, and the axis. Okay, so I might say something like your radius is always equal to f of x minus some number for your axis. And in this case down here, my axis was just 0, right? And so that's why I didn't really need the minus a number here. That's going to happen a lot. There's going to be a lot of times when you don't really need a number there. But if you ever need the number, you just want to know it's there. Okay, So let's try it with one of these. Oh, by the way, I should also mention, we can also spin around the y-axis. So if I was working with this lamp here, I could imagine the y-axis here. And then what I would have to do is I would have to write an equation for this function. I mean, in most of these, you're going to be given the equation, but this is the idea. If we were trying to design this figure, is I would write some equation or some piecewise equation that would give me this function, and then I can spin it this way around the axis. Okay, spin it vertically. But this would have to be a function that's written in terms of y. So I would have to say x equals something with a y in it. Okay, and then we would be integrating with a dy instead of a dx. So I'm sure we'll see one of those. Okay, so let's take a look here. The function y equals 2x over the interval from 0 to 3, there are your endpoints, is revolved around the x-axis. Sketch the solid that would be formed. Well, first let's sketch the graph. Okay. 2x is going to just look like this, right? With a slope of 2. And we are going from 0 to 3. Okay. So we really just have this short diagonal line. Okay. And we're going to take this thing and spin it around the x-axis like this. So what this is going to end up looking like is like a cone, like a sideways cone. So we're going to have it like this and like this with kind of a round outside. Don't judge my artwork and I won't judge yours. Okay. I think that dotted line probably would make more sense on the back, but that's the idea, that this would be our original function, right? This is my x-axis here, and we're rotating it so that it goes around and forms a cone figure. Okay, so that's the volume that we're trying to find. Okay, so to find my volume, I'm going to integrate pi, and then my radius squared, I'm going to just write it this way for now, from 0 to 3. And then I want to think about what is that radius? Well, the radius of any one of these circles, if I were to draw in a circle like right here, the radius is the distance from here to here, which is defined by this function, f of x. And f of x is just 2x. So this right here is my radius, okay, of any one of those circles. So if this is at x equals 1, my radius would be 2. If this is at x equals 2, my radius would be 4. Okay, so we are going to integrate pi, and then from 0 to 3 of 2x, because that's my f of x squared dx. Okay, this one probably wouldn't be bad to integrate by hand, and we should probably do it for some practice. So let's do that. I'm going to kind of ignore the pi here. I'm going to rewrite this thing as 4x squared from 0 to 3. 4x squared dx. Okay. Antiderivative here, I'm going to add 1 and make that an x cubed and then divide. So this is going to be a 4/3 x cubed taken from 0 to 3. Okay. So when I put the 3 in here, I'm going to have pi times, let's see, 3 cubed is 27. Oh, 27 times, well, okay, 3 cubed is 27, but then I'm going to multiply by something over 3. So that's going to be a 9. So I think I'm going to end up with a 36 here. Okay. 36 I'm sorry, 27 divided by 3 is 9. 9 times 4 is 36. When I put the 0 in, I'm going to get a 0. And then my answer then would just work out to be 36 pi. Kind of squeezing it in down here at the end. Okay, so that would be my volume. So that's really it. Hardest part about this is figuring out what your radius is as these things get more complicated. That's the idea. So let's try a couple more. Let's see, where's my next example? Okay, so this one is standing up vertically, and you'll notice that you have x equals y cubed, so this is written as an x equals equation on the y interval from 0 to 4, and we're revolving around the y-axis. So we're imagining our axis standing up and down like this. At the bottom, it's going to be 0, and at the top, it's going to be 4. Okay, I didn't draw my full axis in, but I think you get the idea here. So volume of the solid, we're going to say, let's integrate from 0 to 4. And it's pi times my radius squared. So this time my radius, if I picture my y-axis going up and down the middle here, okay, the radius of any one of these circles is going to be the distance between the y-axis and the outer edge, which is what this is giving me. So this will be y cubed squared dy. This is another one that doesn't look too terrifying to integrate by hand, but we'll cheat and I'll let you use the calculator on this one. So let's see, I'm going to do math number 9, go from 0 to 4, and I'm going to say this is x cubed squared, okay? Notice I did x's instead of y's because your calculator's happier that way. Oh, and then I did forget to put my pi in there, but that's okay. I'm going to just take this number, the 2340.571. And then I can tack my pi on there, or I could go in here and just say, okay, let's multiply by a pi. Okay, so it's 7353.122. Okay, that's it. That's my volume. But again, the whole idea here is just pi r squared. Okay, the region between the graph of y equals 2 plus x cosine of x and the x-axis over this interval is revolved around the x-axis. Okay, really, we could probably do this. I am going to graph it in a second so that we can get an idea of what this looks like. But we could probably set up our integral without it because we have our endpoints, right? We're going from -2 to 2, pi, and then my radius is this entire function. So 2 plus x times cosine x, and then that whole thing squared. And this should give me my answer, even without having the sketch. But let's go ahead and look at it in a graph. Okay, I'm going to go 2 plus x cosine x. I'm going to also change my window so that I'm only looking at it from -2 to 2 because that's all I really care about. Oh, messed something up. Oh, did these backwards. -2, +2. Okay, so this doesn't actually touch the x-axis, but this does give me my limits here. So I would be, starting here and stopping here and integrating this. Looks like it's going to be some kind of like, again, like almost like a vase shape. I could actually shrink up my y-axis too if I wanted to. There we go. That might give me a better idea. And then again, if you kind of imagine the reflection of that over here on the other side of the x-axis, this is going to be very similar to that example we looked at the beginning. But let's go ahead and find our integral. So I'm going to say math. Oh, let me do my pi first. Pi, math number 9, -2 to 2. Since I have my function typed in under y1, I'm just going to go grab that and say y1 squared dx. And there's my volume, 52.429. Okay, let's try another one. This one I want to get to because this one has a different line to revolve around besides just an x or y axis. Okay, so it's not just going to be a 0. So this is actually looking at the same graph, 2 plus x cosine x, rotated this time around the line y equals 3. So I'm going to go ahead in my graph and type in the line y equals 3 so we can take a look at that. Okay, I'm assuming that I probably should have put this in here unless I want to look at my x-axis for just a second. Make this go out a little longer. Okay, so this time, and I realize it crosses again over here, but really I'm looking at this place that's kind of a continuous area with this line y equals 3. So I need to find this intersection point and I need to find this intersection point because we're not using necessarily the same endpoints that we were here. It doesn't specify that, but I'm gonna pull this x-axis out just a little bit more again so we can see the intersection points here. Okay, I'm gonna do a calc intersect. A little closer to this side. First curve, second curve, guess. And my first intersection, oh, it might be because my y-axis is only going to 3. Sorry about this, lots of button pushing, but it's good for you to see the troubleshooting on the calculator. There we go, now we'll be able to see it. There we go. I don't know why that didn't work the first time. So I have an intersection at negative 2.074. And then I need to head over and find my other intersection point. Get closer to this one. Okay, and 4.917. So this is where I'm integrating in between. And this time I'm spinning around this line. Okay, so my radius this time is not based on the location of the x-axis. It's the difference between 3 and the function. Okay, so I'm going to kind of write up here in the corner that my radius is now 3 minus f of x. Now, is it going to be the end of the world if you say f of x minus 3? It's not, because we're going to square it and it's not going to matter. But I only wrote it that way because the 3 is technically on top of the function there. Okay. So we are going to say that my radius, this is pi, and then my radius is 3 minus, and then in parentheses, 2 plus x cosine x. And then this whole thing is being squared because all of this is my radius. Okay. Back here, math number 9. Oh, forgot my pi. This is negative 2.074 up to 4.917. And what I'm doing here is 3 minus the function y1. Notice I put it in its own parentheses though, so I can then square that. And that's my volume, 111.902. Okay, last example. I think this is another vertical one. So this is a vertical line of a function and a vertical line rotating around that vertical line. So let's go ahead and graph this. We're not really going to be able to graph the vertical line because your calculator won't let you, but the function is y equals x plus 2. Okay. And what I want us to envision is a vertical line at this x equals negative 2. So if we have, let's see, here's our xy axis. Okay. And our function, I'll get you some different colors here. Our function x plus 2 looks something like this. And then what we're doing is we're drawing in a vertical line at x equals negative 2. So we're taking this space here and rotating it around this vertical line. Okay, so we're rotating it around this way. So again, going to be like a cone shape. Oh, I'm so sorry. I didn't realize you couldn't see that. Okay. So again, the black lines are my x and y axis. This is my y equals x plus 2. This is the line x equals negative 2. We're taking that space in between and rotating. The fact that it said that the solid has a height of 5 units means that we're integrating from 0 down here up to 5, right? That would give me a total height of 5. So that was a sneaky way of me giving you the limits of integration here. Okay. But since we are spinning vertically, since we are spinning around a vertical line, this is going to be a dy integral. Okay, so we are integrating from 0 to 5 pi. And then this over here is going to be a dy, which means that this equation needs to be written as an x equals so that it's in terms of y. So I'm going to rewrite this as x equals y minus 2. And then my radius is going to be the distance between this function and -2. So my radius is going to be like y minus 2 minus -2. Okay, so it's my function minus my axis. Now, I could think of that as -2 minus y minus 2 in front, like I could do it the other way too, because again, I'm going to square it and it's not going to matter. But this is what's going to happen here is I'm going to end up with y minus 2. Let me move this dy down some. Minus my axis of -2 squared. Now, if you wanted to, you could clean that up some, especially if I was going to ask you to do this by hand, which we could do, because this is really y minus 2 plus 2, which means all of this is going to go away inside here. And what you're really going to be left with is just a y squared. So this is one that I think would be fair game without a calculator, okay? Because this all just simplifies down to a y that's being squared, okay? So antiderivative of y squared would be, let's see, this will be pi times 1/3 y cubed taken from 0 to 5. So we'll have a pi in front. Let's drop the 5 in there. So 5 cubed is 125. So we'll have 125 over 3 minus, when I drop the 0 in there, I just get a big fat 0. And so then we could say our volume is 125 over 3 pi. Okay. And again, we could do that in our calculator if we wanted to. Let's just do that for fun, just to verify. I'm going to do it without the pi. So 0 to 5. In here, I'm going to put in a, let's see, this is going to be an x minus 2 minus -2. And all of that squared. Hopefully I got all my parentheses right here. I think so. And then dx. This, if we turn it back into a fraction, is 125 over 3, and then put our pi back in there, okay, because I didn't do the integral with the pi. So just, again, a way to verify our answer there with a calculator, but assuming here that we did not have a calculator to use. So that's the idea with discs. We're going to do lots more practice with this. We'll introduce washers tomorrow, which just puts a tiny little twist on this whole idea. And then that's it. So we're just about done with the stuff you'll need to know for this course. So nice job with these, and we'll continue to practice these.